Hello everyone, my name is Vivek Bansal. Today I will be presenting my research paper, Layout-Based Vulnerability Analysis of LEON3 Processors against Single Event Multiple Transient Faults using Satisfiability Modulo Theory. Currently I am working as a research assistant at Hardware Verification Group. Also I am pursuing my Master of Applied Science in Concordia University in Electrical and Computer Engineering Department. My main research topics are VLSI design automation, hardware verification, and performing some transient fault analysis. So here's the outline of this presentation. First of all, I will be discussing about the introduction of the transient faults. Then I will go through the background, the inventions, those are already been published before this date. And after that, I will be discussing about methodologies of the fault analysis that we developed here. Then after that, I will be going through the experiment analysis by taking the example of the LEON3 processor as a case study. Then I will show you all the experimental results based on the methodology. Let's talk about the introduction about the transient fault. What is single event transient? Whenever any radiation particle, any high energy particle hit the circuit design at a particular node, what will happen? It will change the logical behavior of that particular component in the design. When the logical behavior of the component is being changed, it is possible that it can change the output of the whole circuit design. The output will be different as per the expected output. In that case, the circuit can fail. As of now, the simulator size has been reduced day by day. So it is possible that whenever any single transient fault hit on a circuit component, it can disrupt more than one number of logical component design. That is called a single event multiple transient. So in that case, we will be discussing about this single event transient fault, how it is going to be propagated to the circuit and how it's going to affect the final output of the design. To check the behavior of the single event transient fault, so we take the LEON3 processor as a case study. So LEON3 processor is a non-proprietary CPU architecture. It is a great for great interest for the embedded designer. It is more accessible and affordable architecture that is available in the market. So this is the reason that we use this processor for the research purposes. So let's talk about the background. The related are available in the same area. The first technique that we have, the radiation testing technique. In this technique, we set up the radiation environment and in which we can perform the radiation testing. First of all, we take the electronic circuit device, then we put that circuit device into the radiation environment. Then we bombard that chip with the high energy particles. Then after that, we check the behavior of that chip at the final output of the design. This technique has two major drawbacks. First, we required a manufactured device prototype. Second, then setup to make this environment is very costly. There's another technique that is called circuit level testing technique, simulation and the formal technique. In circuit level testing, we take the RTL design and we inject some transient fault into the RTL description of the design, and then we check the behavior of that design against those injected fault. If we talk about the simulation, in the simulation we take the RTL description and we check the design against all the possible combination of the input vectors, but it will, if we want to run it for exhaustively, so it will take large computation time, so that is not feasible. So that's the one major drawback of the simulation technique. Let's say if we are going to decrease the number of data input set for the particular design, then it will reduce the accuracy of the verification. In the second technique, in the formal, there are few techniques are available in the formal, but in all those techniques, they don't consider the post layout information in the verification. So in our methodology, we are going to consider the post layout information to check the vulnerability of the design. In our methodologies, we take the RTL description of the design that is written into the VHDL language or maybe Verilog language, and we take the technological library files. In the first step, we perform the synthesis using the design compiler software. In the synthesis, we convert the RTL description of the design to the gate level design. So, when we are performing the synthesis, we try to maintain the hierarchy of the design. It is possible that the design can have the multiple modules inside the whole circuit. So when we are extracting the gate level netlist, we maintain that component hierarchy as well. So in this research paper, we use the LEON3 processor as a case study. So we use the ASIC implementation of the LEON3 processors to perform the analysis. Once we have the synthesized netlist, then we perform the placement and the routing. In the placement and the routing, we generate the layout of the synthesized design. First of all the components, those are being generated into the synthesized netlist, being placed on the circuit layout, and then after that all the components is being routed as per the connections those are available in the synthesized netlist. Once we placed and route all the components, then we extract all the informations. For example, first of all, we will extract the device dimensions from the layout tools, and after that we extract the timing informations that will be utilized later on to include the propagation of the fault. Once we extract all the layout information, then we will extract the SEMT patterns. First of all, we will inject some SEMT faults at the multiple gates at the same time. Then we will check the affected area by that particular transient fault. So after that, we will consider all the logic cells. For example, if we put the fault at a particular node, it is possible that it can affect all the neighbors components as well. So we extract all the logical components that are being covered by the similar surface to be a one single SEMT error patterns. For example, if we have a P as a primary component into the design, any radiation particle hit on this component, it is possible that this radiation particle can affect more than one component throughout the horizontal direction as well as across the vertical direction. So from a radiation experiment, it has been seen that a single radiation particle can affect 3 or 4 maximum number of component into the horizontal direction, and it can affect maximum of 2 number of component into the vertical direction due to the charge sharing across those wells. So we extract all the information based on the circuit layout into the SMT pattern. So all the SMT pattern 3 and that also SMT pattern 4 has been extracted into the one file, and then those information will be utilized when we are checking the fault, how the fault has been propagating to the final output of the design. While we are extracting the SMT pattern, at the same time a SEMT model for each component in the synthesis design netlist will be made. Let's talk about how the SMT model for the NAND gate will be made. So the fault can be propagated to the output of the circuit of any logical component in two ways. First, we can directly inject the fault at the gate, or maybe it is possible that the fault is coming from the previous output of the circuit design. So if there is any previous propagation fault A or maybe B is true, then we will take the values of the fault width and the fault time at any of the input of the design. Then I will check that how it's going to be propagated to the output based on the behavior of that particular component. But if we say that we are directly injecting the fault into the gate with the fault width and the fault time t, then we will see that how it's going to be propagated to the output, and the faulty will be the true, and the fault width and the fault will be time will be calculated based on the circuit behavior. After extracting the SEMT pattern and making the SEMT model for all the logical component in the design, then we will check the fault propagation throughout the circuit with the help of a SEMT solver. For any SEMT fault that has been injected into the circuit, to make it a soft error, so first of all it should reach to the output of the design. That means the injected fault has been reached to the output of the circuit and it change the behavior of the design. To analyze this fault propagation, we assert some assertions by saying that the output is being faulty and we inject the fault width and the time at the particular output. Then we check the circuit against that particular SEMT faults. So with the help of the SMT solvers, we can find some models to give us a satisfying assignments. For those satisfying assignment, if is there any model that is already satisfying model, then we can say that the SEMT fault has been reached to the output. Otherwise, this fault, the injected fault, has been masked due to any of the masking factors. In the last step, then we extract the soft error rate and also we extract the faulty sites on the device layout. So based on the fault propagation, we will mark all these faulty sites on the device layout. First of all, we check the number of satisfying assignment for all the injected SMT faults. So number of satisfying assignments will be provided by the SMT solvers, and we will use the model counting to count these number of satisfying assignments. Then after that, we calculate the propagation probabilities. Propagation probability is basically equal to the dividing the total number of satisfying assignment by total number of the possible input combinations. And after that, while extracting the SEMT faulty pattern, so we will see that if there is a fatal pattern, that means there is no input vector that can mask the fault, then we will consider that fault pattern as a fatal pattern, and then we will mark the device layout to show that these are the most vulnerable region of the circuit. In the experimental part, we took a case study of the LEON3 processor. LEON3 is the Spark V8 architecture based processors that is freely available under the GPL license for the academic research purposes. The RTL description of the LEON3 processor is freely available that can be utilized. So in this design, so we utilize this RTL description and we synthesize that RTL description of the LEON3 at the 65 nanometer standard cell technological libraries. And while we are extracting the synthesized net list, so we maintain the hierarchy of the whole processors. The whole LEON3 processor core has 2012 modules with having more than 6000 K standard cells. After generating a synthesized net list, we place all the components and with the help of cadence and counter tool. So all the component has been placed on the device layout and that's being routed throughout the circuit. While we are extracting the layout information, then there's a limitation in the layout tool that can extract maximum of 50,000 gates. So due to this limitation, so to analyze the LEON3 processor, so we use only the core part of the processors that having the 3 units, integer unit, multiplier unit and the divisor unit. So in these 3 units, the total number of the logical components is approximately 40,000. While extracting the propagation probability for all the injected fault at the particular output, we use the model counting concept to count the number of satisfying assignments. First of all, we start the SMT solvers. Then after that, we assert some assertions by saying the output is being faulty or not. Then after that, we add some assertions by saying that the SEMT fault width and the SEMT fault time has been injected into the circuit. Then after that, we tell the solvers to give us a satisfying assignment for which the fault has been propagated to the output. In the SMT solver, when we ask for the model for which the fault has been propagated, we restrict the input only for that particular output. It is possible that the one input is being affected by only the limited number of input data sets. So in the SMT solver, it will give me the number of possible assignment only for those number of inputs. Once we have all the satisfying count, then we extract the probability of all the SEMT faults that has been injected into the circuit. Now let's talk about the experimental result. First of all, we extract the propagation probabilities against the single event transient fault as well as the single event multiple transient fault 3 and 4. So from this table you can see that the integer unit is the most vulnerable region on the LEON3 processor cores, that having the higher probability as compared to the other two unit multiplier and the division unit. After that, we also try to find the performance of this analysis. So we try to find the analysis time to check its performance. So to build a SMT models, it is approximately taking 50 to 60 minutes, and to perform the SMT analysis for all the components in the design, it is taking approximately 7.5 hours. So in short, it's a total analysis time for the LEON3 core processor is almost 8.5 hours. All this experiment has been run on the high performance computer server, that is a Intel Xeon processor with the 160 core and with the memory of the 1 terabyte. So if we have a more computation power, more memory and more number of cores, then in that case the total time to analyze the processor core can be reduced further. After checking the fault propagation against all the SEMT faults, we will mark the fatal SMT patterns. If there is no single assignment that can mask the fault to reach the output, then we can say that it will be a fatal SEMT patterns. So all the fatal SMT pattern will be extracted and marked on the design layout. So here you can see that all the red colors regions will specify these are the most vulnerable region on the device layout, and this information can be utilized by the engineers when they are designing, when they want to place a transient filter in the process of radiation hardening. Thank you so much for your kind attention. If there is any questions, so feel free to ask me, or maybe later on if you have any questions after this conference, so you can send me an email on this address. Thank you.